Okay, so we've been talking about sound amplitude and the need for the decibel scale. Now we talked about how sound amplitude can be measured by in terms of power values or in terms of pressure units. So if you're measuring in terms of power, we would use the unit watts per meter square. In terms of frequency, we'll use the pascals. So, but however, if we want to use this power and pressure units, we realize that we are limited by a certain range of amplitudes that we perceive as sound, namely the operating limits of our auditory system. In other words, there's only a certain range of watts per meter square, and there's a certain range of pascals that we hear as sound, namely 10 to the power of minus 12 watts per meter square refers to the amplitude of the softest sound we can hear in terms of power values. In terms of pressure, the softest sound we can hear is 20 micropascals. Okay. Anything below those values are too soft for us to hear, to be heard by an average normal hearing listener. However, we can hear a wide range of sounds. Um, So in terms of power values, we can hear all the way up to 100 watts per meter square. So that makes a range of about 10 to the power of 14. In terms of pressure values, we can hear all the way up to 20 pascals. And that gives a range of 10 to the power of 7. So that's just a wide range of amplitudes um, that we can hear as sound. So any sound around us in our environment, like the soft whisper, the average amplitude of speech, um, the sound of a hammer, a jackhammer, all fall within these range. So now we had to come up with a scale that made sense to us. And that's where the decibel comes into play. So for one thing, we need to reduce this wide range into a more manageable range. So an easy way of doing that would be to convert that into a log scale. So that compresses this wide range into a more manageable range. And it made sense to use the log scale because apparently our human auditory system processes sound, an increase or a decrease in sound in a log fashion, both in terms of amplitude and in terms of frequency. As you can see, the frequency being distributed along the basilar membrane over here. So what is a log scale? Log is but the exponent of a base number. So if you have a number such as 10 to the power of 2 is 100, or 10 squared is 100. If you were to convert that into a log scale, that becomes 2. And if you were to do that for different powers of 10, let's say from 0.001 all the way to 1000, if you were to convert that into a log scale, that becomes from minus 3 to 3. So now in this way, we can compress this range of raw numbers from 0.001 to 1000, which would be actually a range of 10 to the power of 7, 10 to the power of 6. If you were to convert that into a log scale, that was more manageable as just 6 values. So the log scale that we use now is named after Alexander Graham Bell. And we call that as a bell. So the bell is actually a log of the ratio between two amplitudes. The ratio is between the amplitude of any given sound. So if you take an equipment that measures sound amplitude, let's say of speech, you're going to be comparing that to a reference amplitude. Okay. And for convenience, this reference amplitude approximates the lowest value, lowest amplitude that we can barely hear. An average normal hearing listener can barely hear. Now again, there's two different ways of measuring that. You can either measure that in terms of intensity or pressure. In terms of intensity, this reference amplitude is 10 to the power of minus 12 watts per meter square. In terms of pressure units, it's 20 micropascals. So you're going to be comparing whatever amplitude you measure to this 10 to the power of minus 12 watts per meter square. If you want the dB in terms of intensity level, or you're going to be comparing that to 20 micropascals if you want the dB in terms of dBSPL. Now, again, there's two different ways of measuring sound: intensity units and pressure units. Okay. Industry manufacturers, manufacturers of sound amplifiers or speakers, they prefer using intensity level units because they can quantify, like, this amplifier has so much watts, and that's what they would prefer quantifying, the output of the amplifier. And they also don't know where you're going to be keeping the sound amplifier, and so they don't know the effect. The effect in this case would be the sound pressure that this sound amplifier or speaker creates. Okay. If you were to measure the effect of this sound amplifier or loudspeaker, then you would prefer using pressure units. The reason for that is the measuring devices we have are fit with pressure microphones. And the device that we use to measure sound amplitude is known as a sound level meter. So sound level meters are fit with pressure microphones that capture the pressure deflections created by a sound. And so it's going to be measuring in terms of pascals. Okay. So if that was the case, then it's going to compare that, whatever the pressure value is, to 20 micropascals before it throws it out as a decibel. So the bell provides a great, a simple way of quantifying amplitude, and it's a functional way of quantifying amplitude. Okay. So it's pretty much the difference between the softest and the loudest sound that the normal hearing person can hear. In terms of intensity level units, that would be 10 to the power of 14. The bell scale that we use dates back to Alexander Graham Bell's founding company, known as a Bell Telephone Laboratory. So the reason why they came up with this scale was to just quantify how much energy is lost when sound are over the telephone loses when it's traveling through cables. Okay, initially they called it the transmission unit, but it wasn't until 1923 when they actually adopted the decibel scale. So when we convert this difference between the softest and the loudest sound that we can hear in terms of intensity level units, namely 10 to the power of minus 12 watts per meter square, the softest, and the loudest would be about 100 watts per meter square. So we get this range of 10 to the power of 14. And when we convert that into the decibel scale, by finding a log of that, we end up with the number 14. So in other words, a human ear can process amplitudes in the range of 14 bells. Now 14 is too small a number, so to make it a little bit more wider, we multiply that by 10. In other words, we find the deci of each of those bell units. We are familiar with the decimeter and decigrams. So pretty much we're multiplying that 14 by 10 to give us a range of 140 decibels. And then we use a notation dB. The small d standing for the decibel, deci, and B standing for the bell. And B is always capitalized because it stands for Alexander Graham Bell. So there's 5 important aspects of the decibel. It involves a ratio. Here we're comparing any given sound to a reference amplitude. Okay. So in this reference amplitude, again, is the lowest sound that we can barely hear if we have a normal auditory system. And that is 20 micropascals if you were measuring in terms of pressure units, and it's 10 to the power of minus 12 watts per meter square if you're measuring in terms of intensity level units or power units. Okay, then it's a log of that ratio. And because we are finding a log of this ratio, it becomes a nonlinear scale. Okay, it's not a linear scale, it's a nonlinear scale. Again, it can be expressed in either in terms of pressure units. So if you're using micropascals, then the decibel that we come out with is the dBSPL. And if you're measuring in terms of watts per meter square, then we end up with dBIL. The fifth point is that it's a relative unit of measure. It's relative because it's based on the lowest sound that an average normal hearing listener can listen to. Okay, average normal human listener, I should say. So because we were finding a unit that's meaningful for the human auditory system, and it's relative to that. Okay, here's a link that takes you to a website where there's some more information about the decibel. Okay, so we end up with dBIL, which stands for dB intensity level, and dBSPL, which stands for dB sound pressure level. Okay, these are based on the average threshold of hearing at one particular frequency. Okay, so when they were devising this decibel scale, essentially what they did was they were trying to find out what's the lowest watts per meter square, what's the lowest pascals that an average normal hearing listener can listen. Okay, so that's how they came up with this 10 to the power of minus 12 watts per meter square, 20 micropascals in terms of pressure units. But these are based on a bunch of average normal hearing listeners when they were hearing for a tone of 1 kilohertz. So they just had one tone. They kept giving it to a bunch of normal hearing listeners and they tried to find out the lowest level they can hear. And again, when you're measuring sound amplitude with a device such as a sound level meter, you can either report the intensity in terms of dBIL or dBSPL. Okay, so now we've converted into a decibel scale. And if you were to report that in terms of dBSPL and dBIL, we can find out what the lowest intensity of different frequencies, all the way from 20 hertz to 20,000 hertz, is required for an average normal hearing listener to barely hear it. Okay, so although we can hear between 20 hertz to 20,000 hertz, within that range, there's only a small, narrow range that we are most sensitive to. So, namely, between 1000 hertz to 4000 hertz. And what do I mean by sensitive? It means that I need it, for the sounds that fall within that frequency range, you require a very low pascals or very low watts per meter square to barely hear it. Sounds that fall below 1000 hertz and sounds that fall above 4000 hertz, you are less sensitive. In other words, you require more intensity of pressure to even barely hear those frequencies. Okay, and it so happens that this 1000 to 4000 hertz is where most of the speech sounds fall within. Okay, somehow we have evolved to be more sensitive to speech sounds. Now that brings us to the question, pretty much the dilemma of the chicken or the egg, whether the auditory system was to begin with was more sensitive to between 1000 to 4000 hertz, and hence we developed speech sounds around that frequency. Or some speech scientists might claim that since speech sounds fall within 1000 to 4000 hertz, our auditory system has become more tuned to that frequency range. But let's leave that argument for those scientists warring against each other. Nevertheless, even though we can hear between sounds of 20 hertz to 20,000 hertz, within that range, we seem to be more sensitive to 1000 to 4000 hertz. So in this graph, we've got amplitude plotted in terms of sound pressure level, so dBSPL, and we are trying to find the lowest dBSPL that's needed for us to hear different frequencies, namely from 20 hertz, the lowest frequency that we can hear, all the way up to 20,000 hertz. So this green line is what we call as a threshold curve. Okay. So, and you can see that it's these mid frequencies where we require very low dBSPL to barely hear it, while frequencies below 1000 Hertz and frequencies above approximately 4000 Hertz, you require a lot more dBSPL to barely hear that. Okay. So the other things that you see in this graph is the concentration of speech sounds, on what we call as a speech banana over here. As you can see that it's kind of concentrated around that mid-frequency range. So essentially, if you were to use a graph that plots in terms of sound pressure level, or dBSPL, and frequency, and if you were to find the lowest level a person, a normal hearing person, can listen to, you would end up with a curve like this. Okay, so showing you again that we hear better at the mid frequencies, and for the lower frequencies and higher frequencies, we require a lot more amplitude. That's good. But if you were to use this plot with this scale, dBSPL scale, it's going to be difficult for us to quantify whether a person has normal hearing or if he has a hearing loss. And if he has a hearing loss, it'll be hard for us to quantify readily what the degree of the hearing loss is, and if the hearing loss is different for different frequencies. So here's another graph showing you the dBSPLs that are important for speech. And as you can see that much of the dBSPLs, much of the frequencies that are input on speech are within those mid frequencies. So here is a graph that we call as the equal loudness contours. Okay, so it's a series of lines that show how loudness changes for different frequencies. Again, look at the graph here. In the frequency scale, we are measuring sounds from 20 Hertz all the way to 20,000 Hertz. And here we are reporting in dB in terms of intensity level. So if you were to do that, you can find again that those mid frequencies we required less dBIL to barely hear a sound. But frequencies below and above that 1000 Hertz and 4000 Hertz range, you require a lot more dBIL to barely hear it. So here are some interesting links. And kind of one of those links, especially this one, you'll be able to play sounds of different dB values, and it'll be a good way to kind of find out how much more dBIL or dBSPL we need to hear those very low frequencies and very high frequencies. While for the mid-frequency sounds, even with a less dB value, you can hear those sounds. So again, that shows that we're more sensitive to those mid frequencies than we are for lower frequencies and high frequencies. And the last curve over here, the top curve, refers to the levels in terms of dBIL that we can tolerate. So this refers to the loudest sound in terms of different frequencies that we can tolerate. So here we've got a threshold curve, the bottom curve, and at the top we have what we call as a discomfort curve, or the UCL curve. One thing you can notice that different frequencies have different thresholds, and they also have discomfort levels. Okay. So what that does to our dynamic range refers to the range between the lowest sound and the loudest sound that we can tolerate. That changes with the frequency. For the mid-frequency sounds, we have what we call as a wide dynamic range. So there's a wide difference between the lowest sound and the loudest sound we can tolerate. However, this dynamic range becomes shrunk or reduced for very low frequencies and very high frequencies. In other words, even though we require a lot more dBSPL, dBIL to barely hear those low frequency sounds, they become loud too soon. Okay, so that reduces our dynamic range. And that's a similar case for the higher frequencies also. We have a reduced dynamic range for the higher frequencies, while we have a wide dynamic range for those mid frequencies. Thus, intensity levels of both hearing thresholds and the UCL varies with frequencies. Okay, so the dynamic range of hearing seems to be very dependent on the frequency of the sound. For the mid frequencies, we have a very wide dynamic range, while for very low and very high frequencies, we have a shrunk, reduced dynamic range. Okay, so now for clinical audiology, we'd like to have a dB scale um, that's easy to measure and relatively is more flat across all the frequencies. So hence the need for the dBHL, decibel hearing level. So this is an example of an audiogram. Okay, so here again we measure only a subset of frequencies, namely from typically from 250 Hertz all the way up to 8,000 Hertz. And we measure that in terms of octave steps, or doubling of frequency. So in a way, we are sampling a person's hearing across these frequencies, and thus we are sampling the person's basilar membrane at different points, going from the apex, where the low frequencies are represented, all the way to the base, up to 8,000 Hertz. So sounds that we find ourselves around in our environment kind of falls within these frequency and amplitude values. Okay. For a normal hearing person, if we were to use a dBSPL scale instead of this hearing level scale, if it was dBSPL over here, your graph will look something like that. It will be you require a lot more dBSPL for those lower frequencies, then it'll curve to low values for the mid frequencies. And again, you require a lot more dBSPL for those higher frequencies. So that's going to be difficult to plot for even for a normal hearing person. And that's going to make it difficult for us if we were to plot hearing levels of a hearing impaired person. So what we'd like to see is a flat line for a typical average normal hearing listener. So what we consider normal hearing is if those person's thresholds are at 15 decibels or better, or in this case higher, above here in the graph. Okay. But based on those equal loudness curves from our previous slides, we see that it's not a we don't hear flat if we were to use a dBSPL or a dBIL scale. Okay. So again, hence the need for the dBHL or hearing level scale. Okay. So when we read a sound in terms of hearing level or dBHL, pretty much what we do is we calibrate the audiometer to give a lot more dBSPL at those low frequencies and a lot more dBSPL at those higher frequencies to make it flat or equivalent. Okay. Because if you do that, if you get an audiogram with a person with a certain degree of hearing loss, we can readily look at the graph, the audiogram, to see how is hearing at different frequencies, low frequencies, mid frequencies, and high frequencies. So this is an example of a person with a bilateral hearing loss. The red markings are for his hearing levels for the right ear, while the blue crosses are those for the left ear. Um, and if we plot that in terms of dBHL, or hearing level, we can readily say that this person's got kind of normal hearing for the lower frequencies, but then sloping to a hearing loss, moderate to severe hearing loss for the higher frequencies. And we can do that only if it's plotted in terms of hearing level, or dBHL. Okay. So our differential sensitivity across different frequencies kind of made the need for different dB scales. Okay. while we have the dBSPL and the dBIL based on the reference values, which is 20 micropascals and 10 to the power of minus 12 watts per meter square, the dBHL, or the hearing level, is based on our differential sensitivity across the frequencies. Okay, so if we convert this dBSPL to dBIL, dBSPL and dBIL into dBHL, or hearing level, we kind of equate or compensate for this differential sensitivity. Okay. So the lowest sound intensity that stimulates normal hearing is what we call a 0 dBHL. Okay. So 0 dBHL refers to the sensitivity of a normal hearing person no matter what the frequency is. Okay. So for us to do that, we need to give different dBSPL values depending upon the frequency. For example, for 1000 Hertz, we require only 7 dBSPL to equate 0 dBHL. But for frequencies low, such as 250 Hertz, you'll have to give a lot more dBSPL to equate that same 0 dBHL. And if you do that, we can convert this dBSPL scale, which is kind of like this graph over here, where we hear differently at low frequencies and very high frequencies than we do in the mid frequencies. In other words, we require a lot more dBSPL for the low frequencies and mid frequencies, and low frequencies and the high frequencies than we do for the mid frequencies to convert into a dBHL scale. So the audiometer, what it does is pretty much when you calibrate it, it puts out a lot more dBSPL for lower frequencies and for higher frequencies than it does for those mid frequencies. So for mid frequencies, you might give like 7 dBSPL for 1000 Hertz. And if it was a typical average normal hearing listener, he's going to hear that sound at 0 dBHL. While for, let's say, 250 Hertz, the audiometer is going to actually put out 25.5 dBSPL, but the person is going to hear it at 0 dBHL. Okay. So audiometers actually measure intensity in terms of HL, our dB hearing level. Okay. So they already account for our differential frequency sensitivity by putting out more dBSPL for low frequencies and high frequencies, and putting out lesser dBSPL for those mid frequencies. So if an audiometer is calibrated in terms of dBHL, a typical average normal hearing listener should be able to hear all the frequencies at 0 dBHL. Okay. And there's a range what we consider normal if they can hear if this person's thresholds falls between 0 dBHL and 15 dBHL, we consider that to be hearing within normal limits. Okay. So again, to recap, we've got 3 dB scales we've talked so far: the dBSPL, sound pressure level, dBIL, intensity level, and dBHL, hearing level. The first two, dBSPL and dBIL, are based on pascals and watts per meter square, respectively. Okay. Those are the units that an equipment measures for users to measure sound amplitude. Okay. And if we were to plot in terms of dBSPL or dBIL, you would end up with a threshold curve like this one, which showing again that we hear poorly or with less sensitivity for those low frequencies and high frequencies. We do much better. We're more sensitive to those mid frequencies. Okay. In clinical audiology, we would like a scale where we hear pretty flat across all the frequencies. So you calibrate your audiometer to put out different dBSPL or dBIL values so that we can have a flat dB scale across all the frequencies. So hence the need for the dBHL, or hearing level. Okay. Now if you were to convert the dBSPL into dBHL, now we would get an average normal hearing listener listening to 0 dBHL listening to the different frequencies at 0 dB HL. Okay. There's one more dB scale that we use in clinical audiology. That is the dB sensation level. Okay. In some applications, we might want to give, let's say, a material like speech at the same hearing sensitivity level for different listeners. Okay. For example, one of the common tests that we do in speech audiometry is the speech recognition testing. In speech recognition testing, we want to give a list of words at a comfortable level for this listener, for the person we're testing. Okay. And what we consider comfortable in is if we give the speech material 40 decibels above the lowest level, they can barely hear that speech. Okay. So to begin with, we're going to find what is this lowest level that this person can hear speech material. And so we use a measure known as a speech reception threshold, or SRT. So here we give a list of words and ask them to just repeat them, even if it's very soft. And then after we found out what's the lowest level they can hear the speech material, we want to give a list of words to do the speech recognition testing. Okay. So let's say you might use a list of 25 words, for example, and we want to find out how many of those words this person got correct. Okay. So when we're doing that, we're going to set the audiometer 40 dB above that person's threshold. Okay. So in other words, we're giving this material at 40 dB sensation level. Okay. Um, so here the reference intensity level is a person's individual threshold. So you might have a person with normal hearing where he might hear those words at 0 dB HL. For him, we would be giving this list of words at 40 dB HL. Okay. Then you might have a person, let's say, with a mild hearing loss. So he begins to hear those words at 30 dB HL. So in this case, we'll be giving this list of words 40 dB above that. So your audiometer is going to actually read 70 dB HL. Okay. So here, what I mean by threshold is if they can hear this tone or speech about 50% of the time. Okay, and so this number of decibels of a sound above this person's threshold would be the number of dB sensation level. So for a person with a 5 dB HL threshold, let's say 1000 Hertz, you're going to be giving the sound, if you were to give the sound at 50 dB HL, that means that it's 45 dBs above his threshold, hence 45 dB sensation level. The same tone, if you were to give to a different person whose threshold is 20 dB, then this 50 dB sound, 50 dB HL sound, is going to be heard at 30 dB sensation level. Okay. Thus, we have three main dB scales. We have the dBSPL, that corresponds to what is reported by the sound level meter. Sound level meters, as I said, are equipped with pressure microphones. They measure pressure deflections. And it's going to report in terms of dBSPL. Okay, so it's going to do the log conversion, and when it displays in the display, it's going to display the sound amplitude in terms of dBSPL. Now the reference for this calculation would be the 20 micropascals, which refers to the lowest amplitude that an average normal hearing listener can listen to. And we've figured out that when we tried to find how much dBSPL even a normal hearing person requires to hear different frequencies, we found out that for very low frequencies and very high frequencies, we require a lot more dBSPL to even barely hear a tone, while we seem to be more sensitive to those mid frequencies, which require less dBSPL values. And this is a standard value. So when you're measuring like the output of an amplifier or a speaker, typically they report in terms of dBSPL. But for clinical audiology, we needed a scale that kind of equates for that differential sensitivity we have for different frequencies. So hence we adopt the dBHL, a hearing level scale. And this corresponds to the audiometric zero. Okay. So here we require different dBSPL values uh, for different frequencies to even barely hear it. Okay. So the dB values listed in HL represent the energy levels required for a normal hearing person for that particular frequencies. And there is standard conversion values to convert from dBHL values to dBSPL, and vice versa. So here is an example of the dBSPL values required to convert into dBHL values. And as I said, it changes depending upon the frequencies. For low frequencies and for high frequencies, you require larger dBSPL values, while for mid frequencies typically require lower dBSPL values. And the standard conversion values is also going to depend upon what transducer or what device you use to deliver the sound. Okay, so here's two different ways of delivering what we call as air conduction sounds. One is a earphone, and the other one's an insert earphone. Um, the standard earphone is also known as a supraoral earphone because it sits over the ears, supra. Insert earphones are the ones that are delivered inside your ear canal. Okay, the third scale that we use is the dB sensation level. And this is desirable when we are testing a heterogeneous population with different levels of hearing levels, okay, but ranging from normal all the way to profound hearing loss. Now here we want to test these individuals with the different hearing levels at at a value at a level that makes sense to them. Okay, so we want to present these words, for example, um, where it's comfortably loud for them. Okay, so again, an example that we used was for the word discrimination testing. We want to present those words at 40 dB above the lowest level they can hear those words. Okay, so in a clinic you might say that I'm going to do word discrimination testing at 40 dB sensation level, no matter what this person's threshold is. Okay, so for a person with normal hearing, let's say 0 dB HL threshold, you're going to give those words at 40 dB. If this person's threshold is 40 dB to begin with, in other words, he just starts hearing those words at 40 dB, you actually will be doing this testing 40 dB above that, let's say at 80 dB HL. So here you're presenting it depending upon the person. You're presenting those words at the equal sensation level. Okay, that's with respect to the decibel scale. Okay, another kind of interesting effect that I'd like to talk about in terms of acoustics is this Doppler effect. Doppler effect is observed when a person when a sound source is moving with respect to an observer. Okay, it's described as what happens when there's an upward shift in frequency when the source is moving towards observer, and it appears there's an apparent downward shift in frequency when the source is leaving or receding from the observer. And you might have encountered this um, when you hear a siren of, let's say, a cop car, and you're going on the highway, and you hear a cop car coming from the back. After the initial fear of checking your speedometer and making sure that you're not speeding, you probably would notice that the pitch of the siren, the cop siren, getting more shrieky, more high pitched as a car approaches you. And when the cop car moves away from you, you might notice that the pitch of the siren getting lower, lower pitch. Okay, and that's what we call as a Doppler effect. And a good way of, well, I think a good way of explaining the Doppler effect is with this analogy of a bug stuck in the middle of a circular pond. with with it making waves at the rate of, let's say, 2 hertz per second. In other words, making two concentric waves every second. Okay. Um, in this analogy, if this bug was to say move towards an observer, let's say B over here, and with its paddling its legs at the rate of 2 hertz, um, when it's moving towards B, you'd see that those waves get more congested or concentrated. Um, while if you have another observer at the other end, say, let's say this observer is A, you would see that these waves get more spaced apart. Such is the case for the sound that's created by a moving sound source. If it's moving towards a listener, those sound waves get more congested. In other words, uh, it seems that these sound waves wavelength is shrunk, so they have smaller wavelengths. While if the same sound source is moving away from an observer, those sound waves seem to be more spaced apart. In other words, they seem to have long wavelengths. And we know that sounds that have small wavelengths are heard as a higher pitch sound, while sounds that have a longer wavelength are heard as a lower pitch sound. And that's what happens. So if a sound source is moving towards an observer, it seems like the sound is getting more higher pitched um, for that observer, and the sound source is moving away from an observer, the same sound is heard as a lower pitched sound. Okay, an important point to make is that it's not that the cop car is making it purposefully high pitched as he's approaching you, or is making it low pitched as he's moving away from you. The frequency of the siren remains the same. That's why we call it as an apparent shift, because just because the sound source is moving, it seems like the sound is becoming higher pitched, while when it's moving towards you, and it seems like it's becoming a lower pitch when it's moving away from you. Okay, and you probably might have heard the Doppler effect being used in different ways. Uh, it's used actually by the bats. Actually, they can figure out whether a bug is moving towards them or moving away from them based on the change in the pitch they hear of that bug. Um, and the Doppler effect is also it's used by like weather stations. So now they actually they can figure out whether those water-bearing clouds are moving towards you, or the storm is moving towards you or away from you, by using these Doppler radars. They see a change in the wavelength um, of the light coming from the clouds.